editing and whatnot. So extremely diverse applications. Just download the relevant app and do your work. But PLC is not a generalized piece of equipment. It's not a generalized computer for a specific application. And what is that specific application? It basically is for automation applications. Automation of what? Of either a machine or an equipment or a process that you find in a factory or that you find in a process plant. The application domain of a PLC is very well defined, unlike your laptop or your computer. And that brings in a basic difference in hardware. Since it is meant to be used for automation in an industrial environment, it must be capable of connecting to a wide variety of sensors and actuators, input devices and output devices. Input devices could be sensors. Input devices could also be simple switches. A push button is an input device. It's not a sensor. It's manually operated, but it's definitely an input device. You have all kinds of sensors are possible. Limit switches, proximity sensors, both of which sense position, temperature switch, level switch you've already seen in that tank application. It could be a flow switch. It could be a speed switch, whatnot. So you could have all these kinds of sensors and input devices that are actually sensing different parameters within a process, within a machine, within an equipment that you're trying to control. So all these sensors need to connect to your PLC because they provide you with all the input information based on which you perform your automation or based on which your user program is executed. Also, it needs to connect to all kinds of output devices. Output devices could be simple lamps. It could be an audio alarm, just like you did in the case of your tank filling system. You had a lamp blinking. You had an audio output possibly. It could also be output devices, actuators. Now, actuators, for example, you had your pump being operated by the PLC. It was being turned on or turned off. That is one output device. It could be a solenoid valve, or it could be control valves that have an analog output. So you could have various kinds of devices. It could be a motor being turned on or turned off. So again, the PLC must have the ability to directly connect to output devices and directly connect to input devices. So that is what makes a PLC different in terms of hardware compared to either your laptop or a smartphone, because a laptop or a smartphone is not designed to connect to input signals or output signals. Of course, you could connect your laptop or computer to a switch, to an input signal, but for that you need additional hardware. You directly take a laptop, directly take a computer. It's not capable of interfacing to a switch. It is not capable of directly driving an indicator. You can do that, then for that you'll require additional hardware. So this is one area where your PLCs are significantly different from your general purpose computing devices. Another important requirement in the case of PLCs is, since it is used in an industrial environment, say for example a power plant. A power plant runs on a continuous basis for obvious reasons, 24/7. So and say that is being controlled by a PLC. So if something goes wrong with a PLC, what happens is ultimately your PLC is controlling that particular process or equipment. So if your PLC doesn't work, your plant doesn't work, you have a shutdown, and you could have serious implications. So, I mean, no one can rule out that your hardware will never fail. So what do you need to do? In case it fails, it is extremely important if your laptop fails, no problems really, because I still, even today, I've got a message from someone from a class who says that his laptop is not working since the last 3 months, and that is the reason for everything. Okay, fine. You can have a laptop not working for 3 months, but you cannot have a PLC not working for 3 months and a plant being shut down for 3 months. So what is extremely important in case of such equipment is you need to reduce downtime. Downtime means the amount of time for which your process is not operating. So if something goes wrong with the PLC, no one can rule that out. There must be means of one, quickly identifying what has got wrong. I mean, you don't have the time to remove your PLC, send that to the vendor. Vendor means the person was the company was made it. They troubleshoot it, rectify it, and send it back to you. No, that's not the case because you simply don't have that amount of time. So there should be means of quickly identifying what has gone wrong, and once that's identified, quickly replacing that part of the PLC. You always have spares. Spares means just like you have an additional tire within your car or truck or whatever. If one tire something goes wrong with it, you just replace it with a second tire. So that's a spare. In case of a PLC, all important components you have spares. You have additional components that are stored. So if one of the components is not working, you simply replace the component and a PLC is again back to normal. So that way you reduce downtime. But what is important, there should be means of clearly identifying what's wrong, and there should be means of quickly replacing that so that downtime is reduced. That's a very important consideration when it comes to PLC hardware. We'll see how that is implemented. And of course, you obviously require a programming device, which probably is quite different. You don't have a separate programming device in either a smartphone or your laptop. A programming device obviously is necessary because firstly, any PLC has a user program, the program that you want to implement within a PLC. So you've got to write that particular program. And that program, once written, once established, once a functionality is established, once you're sure that it works the right way, you got to download this particular program within the memory of the PLC. I mean, that is precisely what you've been doing so far. You have a laptop which runs a CodeSys-like environment, which is a development environment. It could be CodeSys, it could be Siemens DIA portal, it could be RSView from Allen Bradley. They're all similar computing requests. That is when you write a code. After that, you compile it. Here you say you build, and after that you go online. Online basically downloading a compiled program into the memory of the PLC, which will ultimately execute this particular program. So for this entire exercise, you need a programming device. And second, maybe the software is not working the right way. Maybe it's not doing what you want it to do. So you need to debug the software. That is always necessary in case of complex programs. No one uses a PLC to write the kind of programs we have been writing in this particular lab. That is too simple, too trivial. Real life programs are far more complicated. So obviously you're going to have others once you write the program. So what is done is this PLC, this programming device is connected to your PC and it's execution in real time. You can see all the contact that are not conducting, what is the state of the outputs. So you can actually see how you're programming in real time, and then probably you can find out bugs, rectify that. So for all the programming device. So any PLC essentially needs a programming device, and how is the programming device connected? The programming device is to this interface. Here it's got an RJ45 connector. Your computer, desktop computer has got an RJ45 connector. As of today, a PLC is also provided with an Ethernet interface as a standard option. So that Ethernet interface on the PLC and the Ethernet interface on your laptop or your desktop establishes a connection between your programmer and your PLC, and then you can write a program, download it to the PLC, and see a program executing in real time. Earlier, you had different communication protocols because as of today, all PLCs use an industrial variant of an Ethernet. I'm not going into the details of what industrial Ethernet is, but it's just a variant of the Ethernet that we use in our day-to-day lives. Okay, so the block diagram of the PLC mounting system, I'm just coming to this a little later. Very obvious, you need a power supply. What does a power supply do? Takes a main supply to 20 volts or 110 volts, depending upon the country, and typically converts that into two levels. One level is 24 volt DC. Why 24 volt DC is important? I'll come to this very shortly. And second is a low level DC voltage, which is used for the operation of all the processors and all the electronics that goes into the PLC. Earlier days that used to be 5 volt, but presently no processor works at a 5 volt level. They operate at lower voltages, 3.3 or even less. It could be even 1.8. So all the necessary supply voltage that is required for the operation of the hardware is generated by the power supply from the main supply. Processor, fine again. But then when you talk about the processor, whenever you are buying a PLC, you have multiple options of processors. Exactly the same way you have options when you're buying a laptop, you have options when you're buying a smartphone, right? You can buy a low-cost i3 processor for a laptop with the i3 processor. You can go for an i5 processor. You can go for an i7 processor. And probably smartphones, you have different types of SoCs from either Qualcomm or MediaTek. Now, the difference is price versus performance. Exactly the same thing in case of a PLC processor. You have multiple types of processors that you can select from. The difference is high performance level, high price, low performance, low price. So whatever suits your requirement the best is a processor that you choose. Then you have, of course, processor also includes memory, just like you can choose amount of memory. The memory here is RAM and non-volatile. Non-volatile memory is always flash memory, exactly the same way it is in case of a smartphone. You don't have hard disks in case of a PLC. It's essentially a flash memory, solid state non-volatile memory. So again, just like in a smartphone, you can say I want 32 GB, I want 64 GB, depends upon your requirement. You can further expand that using an SD card. All the options are equally valid in case of a PLC as well. Now is the communication interface. Communication interface, as I said, there are various requirements why you need a communication interface. That is, communication interface is an interface by PLC talks to some other device. The basic requirement, you always need a communication interface because you always need to connect a PLC to a programmer. You can't have a PLC being functional without using a programmer. So for at least for connecting the programmer, you require a communication interface. You also require a communication interface, for example, if you want to connect a display. Display is not an integral part of a PLC, unlike say a laptop. Your laptop always comes with a display, but a PLC does not as an integral part come with a display. Of course, you can order out a separate display. Why? For displaying a visualization, more commonly referred to as an HMI. But then that display hardware will have to be connected to your PLC hardware. Exactly the way we have in case of a in the desktop. In the desktop, your computer, that particular black box or whatever that box is, you have to separately buy a modem gets connected to your computer using some kind of an HDMI interface or whatever. It's the same concept here. You have a separate display device. It's optional. But if you have an HMI, if you have visualization, you've got to buy this display device. It typically looks like a notepad. Typical screen size is 8 inches to 10 inches. But what is important is it is made for industrial use. That means it's extremely ruggedized. Typical classifications is IP65. Probably you don't understand. One IP65 means is 6 is a protection against dust. 6 means it is dust proof. And 5 is it is waterproof. Waterproof doesn't mean that you can put it inside a bucket of water. You can immerse it under water, no. But if you splash water on that particular device, even by a hose, nothing goes wrong. High-end smartphones these days, whether you buy it from Apple, Samsung, etc., they are all IP65 to IP66, which means that you can take your phone inside a swimming pool, even 3 meters down inside a swimming pool. Nothing will go wrong with the phone. That is guaranteed by the manufacturer. Anyway, what I'm trying to say is such display devices differ from your laptop display or your computer monitor in terms of the ruggedness, in terms of its ability to withstand hostile environments, high dust levels, high humidity, water levels, or whatever. So again, to connect this display to your PLC, you need a communication interface. The third requirement is you could have multiple PLCs. In a large plant, you don't have a single PLC controlling the entire plant or all the machines in a particular plant. You have multiple PLCs, each controlling a small section of the plant, each controlling one particular machines or probably 2 particular machines. And then all these PLCs in turns are connected to a local area network. So how do you connect a PLC to a network? Exactly the way you connect computers to a network. Again, use Ethernet, you have a switch, again, industrial grade, which ultimately connects all these PLCs together so that you can have a transfer of data from one PLC to another PLC, or you can transfer data to a centralized HMI. That means I have a centralized large screen which takes data from all individual PLCs and provides a centralized display of what is happening where in this particular plant. All information from the plant is displayed at a centralized point. How is that possible? That's possible by connecting all PLCs on a local area network. And for that, you need a communication interface in the PLC. So there are multiple reasons why you need a communication interface in the PLC. And as I just mentioned before, the standard option as of today is and industrial Ethernet option. Finally is the most important part, the input and the output interface. This is what makes a PLC different from all other general purpose computer systems. Now, inputs and outputs. Inputs are interfaces which allows the PLC to connect to various kinds of sensors and input devices. Output interface is the hardware which allows the PLC to be connected to various kinds of lamps and output devices. Now, inputs and outputs could be broadly classified into, well, this is a typical monitor, industrial monitor, where you see the HMI part or the visualization part. Okay. Now, this table input outputs of a PLC. There are two major classifications: digital or discrete I/O, whatever you call it. Both names are equally popular. And second is analog I/O. Again, discrete I/O could be of two types. It could be an input, it could be an output. Discrete means any signal that could only have two possible states, 0 and 1. Analog is a variable that could continuously change. So your switch is a device which provides a discrete output. Your lamp is a device that operates out of a discrete output, because a lamp can have only two states, a switch can have only two states, and so on. Analog IOs are basically devices where the variable is an analog variable, can change continuously. For example, the signal from a transmitter. Transmitter, is internationally standardized to a 4 to 20 milliampere signal. It can change continuously from 4 to 20 milliampere. So that's an analog signal. So if you want that particular signal to be connected to a PLC, you require what is known as an analog input. And say you are trying to control a pneumatic actuator or electrical actuator, whatever. In case of a pneumatic or electrical actuator, the position can continuously change from 0%, which is fully closed, to 100%, which is fully open. Again, that is an analog variable. So in order to connect a PLC to a pneumatic actuator to an electrical actuator, you'd require what is known as an analog output. Okay, now going into the details of it, because this is the most important part which segregates or differentiates a PLC from other computers. First of all, coming to digital inputs. This is a very small PLC, very simple PLC. Just what has been shown is you have multiple inputs. Here, what's shown is you have two inputs. These are input devices, but both of them, one is a switch, another is some kind of a sensor. It's a limit switch. This is a sign of a limit switch. So these are two-state devices. A switch could be open or closed. A limit switch again could be open or closed. Whenever you say it's a switch, it's basically a two-state device. So these signals are being fed to the input interface of a PLC. So what's the job of this interface? The job of this particular interface is to convert the input signal obtained from a sensor. Here the device is, you have got one sensor hardware which converts the signal from the input device or the sensor into something that is compatible with the logic levels of your processor. Let me repeat this. Converts the signal from the sensor, the two-state signal from the sensor or the input device, into a level that is compatible with the logic levels of your processor. You've studied about ETL in a digital electronics class. There you know that the two logic levels are represented by voltages. Ideally, one is 0, the other one is 5. But as I said, 5 volts is no longer in use. We have gone lower down the voltage scale. So next one is probably LVTTL 0 and 3.3 volts. Now you have 0 and 1.8 volts. Fine. But say I've got a switch. Now this switch, when I press, remember, a switch is basically a contact. A switch by itself does not generate any voltage. This is an important thing that you need to put into your mind. Any sensor like, say, a limit switch, a push button, a proximity sensor, a temperature switch, flow switch, level switch, whatever, they're all basically switches. They just have a contact, electrical contact, which is either open or closed. A switch by itself cannot or does not generate a voltage. But for a PLC, the input is represented by two voltage levels. For any digital system, the two input states are normally represented by voltage levels. For TTL, as we know, that is represented by 0 and 5 volts. In case of a PLC, these two levels are represented not by 0 and 5 volts. It is typically represented by either 0 and 24 volt DC, that is logic high is 24 volt DC, logic low is 0 volt DC, or logic low is 0 volts, logic high is main supply, that is 220 volt AC is logic high, 0 is logic low. That is one popular way of representing the two logic levels. The second popular way of representing the two logic levels is logic low 0 volt DC, logic high 24 volt DC. Now, why do we use such high voltages? Why not 5 volts? Why not 3.3 volts to convey the status of a switch or some device to the PLC? The simple reason is a PLC operates in an industrial environment. Industrial environments are extremely noisy. Noisy means I'm not talking to audible noise. I'm talking about electrical noise. Whenever you have large motors or welding machines or large heaters operating, you typically have all these operating in an industrial environment. What happens is large amount of electrical noise. Noise is any undesired voltage that is induced in a signal path. Even in a normal lab environment, you just take an oscilloscope, connect a probe to it, and hold the tip of the probe by your hand. You'll find that you're an extremely good sine wave generator, and that sine wave happens to be exactly 50 hertz. It's picked up from the neighborhood power supply lines, but you'd be surprised that you generate a wonderful 50 hertz waveform. The amplitude could be as high as even probably 1 to 1.5 volts. You've done nothing. You've not connected any signal to the oscilloscope. You just are holding the probe input by your hand. You just place the probe close to a power inlet point. You'll find that huge voltages are induced from nowhere. So what is that? You have not applied any voltage, but still you have unwanted voltages in that input of the oscilloscope. So that is noise, any undesired voltage in the signal path. In an industrial environment, one is because of large amount of electrical noise that is present, and second, the sensors could be remotely placed from the PLC. The push button or any sensor, temperature switch, level switch, for example, in a tank when you're sensing levels, you have two level switches. You've done that particular assignment. So where's your tank? Tank probably is in a rooftop. So there on the rooftop, you have two level switches. You can't put the PLC on your rooftop. It's not logical to have a PLC directly in the rain and the sunshine. You'll put PLC somewhere down within your house. So you need to wire the two level sensors to the PLC. So what happens is the two sensors are remotely located from the PLC. So when the sensors are remotely located from the PLC, you have long wires between the sensor and the PLC. And when these wires are located in an extremely noisy electrical environment, what happens is significant unwanted voltages, what is electrical noise, is picked up. Now, if your two levels is 0 and 5 volts, what could happen is the noise level could become comparable to that 5 volt level, and it could result in the actual signal being lost. So the idea is the actual signal should be much higher. Make it 24 volt DC or make it just 220 volt AC so that the noise magnitude becomes relatively smaller compared to the signal magnitude. I can't reduce noise. So what am I doing? I'm increasing the signal level so that signal to noise ratio remains significant. I can't reduce noise in an industrial environment. I can't say that I'm not going to have any motors. I can't say that I can't have any welding machines. They're all there. They are going to generate noise and you're going to pick up noise. No way that you can avoid that. So what do? Instead of using 5 volts, instead of using 3.3 volts, increase your signal level so that your signal becomes significantly larger compared to the noise level. So that's the reason why the two logic levels is either represented by 24 volt DC or 220 volt DC, which is even higher. But no processor is capable of operating at 24 volt DC. All processors have ports, as you know, IO ports, and there you apply a voltage to signify 1 and a voltage 0 to signify logic state 0. But those two voltage levels is typically 5 volts earlier, now 3.3 or lesser. So what you need to do is you need to convert the 24 volt DC input that comes from a sensor, or you need to convert the 220 volt AC that is coming from a sensor into a 3.3 volt level or 1.8 volt level, which is compatible with your processor. So the first job of the interface, input interface, is to perform this translation. High voltage, either DC or AC, converted into a lower level DC voltage, which is compatible with your processor. That is requirement one. The second requirement of the input processor, as you can see, input interfaces. Normally, as I said, a very important requirement in case of PLCs is the ability to diagnose any fault, so that if something goes out of order, you need to replace it. It's a standard practice that all input interfaces are provided with an LED status display. Here, it's symbolically represented that these circles, one of them is red, these are basically LEDs that is associated with each input interface. That is, if the input status is 0, that is off. If the input status is 1, that particular LED lights up. So if you know that some sensor is working and you find that this particular LED is not lit up, you immediately get to know there's something wrong with your wiring or probably the input interface. There's something wrong, it's not working the right way. You need to replace the input interface. So again, to diagnose any fault in the input interface, standard practice is to provide input indicators or LED indicators. So that is a second job, is to provide status indication of all the inputs. A third very important requirement is to provide galvanic isolation. I'm not sure whether you've heard about the term. Galvanic isolation means, or electrical isolation is also used. What it means that you're conveying a signal from point 1 to point 2 without any kind of electrical connection between the 2 points. You have point 1, point 2, the signal is being communicated, transferred from point 1 to point 2, but there is no electrical continuity between point 1 and point 2. How do you do this? There are two standard ways. One way, as you already know, is to use a transformer. Transformer, if you apply a voltage to the primary, you get a voltage at the secondary. Of course, it depends upon the turns ratio and all that. But as you know, in a transformer, there's absolutely no connection, electrical connection between the primary winding and the secondary winding. The signal is transferred from the primary to the secondary by magnetic coupling. Electrically, if you measure the continuity between the primary and the secondary of a transformer, it will show that it is open circuit. That is isolation. But the problem with the transformer is that it only works with AC signals. Transformer doesn't work with DC signals. But here my two logic states could be represented. For example, 24 volt DC is a valid high logic state. So if you apply 24 volt DC to a transformer, the transformer does not work. What's the second approach? The second approach, and the approach that is most commonly used, is something called optical isolation. And that is something like this. This is a, what should I say, simplified block diagram of what exists inside an input interface. This works both for AC inputs, that is where a logic high is 220 volts or 110 volts, depending upon the power supply used in that country, or it could be 24 volts. What you have is, of course, this one full wave rectifier. In case of AC, this is required. You convert this into DC signal. Then you have filters. Why filters? One, it's a low pass filter. The basic purpose of the low pass filter is to eliminate any kind of noise or surge that could be present in this input signal. Plus, you have protection against surges that could be achieved by Zener diodes, that could be achieved by metal oxide varistors, whatever. I'm not going into that details. But what you're basically doing is, if you have an AC signal, convert that into DC. That's function one. Second, have an signal conditioning circuit, which is simply a low-pass filter for suppression of surges, plus additional hardware for suppression of noise and surges. After that, what you see is the most important part, this thing, this rectangle, that is what is called the optical isolator. It basically consists of a combination of an LED, not actually an LED. As of today, it's an IRED is more commonly used. That is just like an LED, but instead of visible light, it emits infrared radiations. And on the other side, you have a phototransistor. So if you drive current through this LED, the LED is lit up, it generates light that falls in this phototransistor. And the phototransistor, what it does is when light falls on it, that phototransistor goes into a saturation mode. And if there's no light falling on it, so this particular light acts as a base drive. So if you have light falling on the phototransistor, it is driven into saturation, the phototransistor conducts. If you have no light falling on the phototransistor, then it's in the cutoff mode. So this phototransistor is either conducting or in the cutoff mode, depending upon whether you're driving current through the LED or not driving current through the LED. So if you drive through the LED, the phototransistor is conducting, so the signal is conveyed from the input side. Look, there's absolutely no electrical connection between the LED and phototransistor. two completely independent devices within a housing with a common casing. If you measure continuity between the electrical information, here is optically coupled between the input to the output. And transformer, it's magnetically coupled. So this is galvanic isolation, that is, you convey information from the input to the output, and the output in turn connects to the processor. After this phototransistor, you basically have a circuit which connects to the I/O ports of that particular processor. So that way, the whole idea of having this optical isolation is, if you have surges, if you have significant noise on the input signal, those is not allowed to appear at the input of the processor, because remember, the processor as of today operates of extremely low voltage levels, typically 1.8. So you simply cannot afford any surges, any noise that is present on the input signal to appear at the processor input output ports. So that is primarily why you have this particular galvanic isolation. So this is a typical circuit. The bridge wave rectifier may be present, may not be present. Depends upon whether an AC input or DC input. Then you have devices to condition the input, that is basically a low pass filter. Then you have devices, hardware devices, to restrict or limit surges and noise voltages. A stage of optocoupler, that is galvanic isolation between the input and the output. What is not shown, you also have an LED which displays, which is shown on the top, this power logic LED. This logic LED is basically the LED that is provided besides each input channel, which displays the logic state of that particular input. So this is a typical block diagram. As you see, bridge rectifier followed by noise and debounce filter. You know what debounce is. BD has taught that extensively. Threshold level detection. Threshold means, so okay, 24 volt DC is high, but it's not exactly 24. There will be a band, say 0 to something like 5 to 6 volts is logic level low, and something from 18 to 24 volts is logic level high. So anything in between, say you put the threshold at something like 14 or 15 volt DC. Below that is logic level low, above that is logic level high. So it defines or determines the threshold above which you have logic level high and below which you have logic level low. So that is what is a threshold detector, followed by an isolator, galvanic isolation, followed by the logic, which is basically the circuit which connects to the processor. This is a typical diagram of an AC or DC input interface. Now coming to the most important part, as I just said, see, for the PLC, logic level high is 24 volts or 220 volts. Logic level low is 0 volts. But your switch, any kind of proximity sensor or limit switch or level switch or temperature switch, none of these devices generate a voltage output. Remember, they are switches. They just have a contact which is either open or closed. So how do you convert the status of a contact into a voltage? Because a PLC does not understand the state of a contact. All it understands is, if I get 24 volt DC, it is logic level 1. If I got 220 volt AC, it is logic level 1. If I get 0 volt DC, it is logic level 0. But your switch, your push button is not generating any voltage. So you have got to convert the state of your push button. That is, you've got to convert the state of your contact, open contact or closed contact, into two different voltage levels. How do you do that? As you have guessed, simple, just connect a voltage source in series. Look at this. You have two devices. Top is a hand switch. That is any kind of push button or button. And below that, they have shown a pressure switch. This could be any sensor. It could be a pressure switch, temperature switch, limit switch, flow switch, whatever. So what you basically need, these are the inputs of the PLC. They have shown multiple channels. Of course, the PLC has multiple input interfaces. You always need to connect multiple input sources to the PLC. So what you do is take a DC supply. DC supply when? If this particular input interface is rated at 24 volt DC. And if the input interface is rated at 220 volt AC, then this does not become a DC supply. This is a main supply. So take this supply and connect your device, which is either a switch or a sensor, in series. So what happens is, when the contact is closed, this voltage appears at the PLC input, and that is interpreted as logic 1. And if the switch is open, if the sensor state is open, the contact is open, then this voltage does not appear at the input of the interface. So the voltage at the input interface is 0, and that in turn is interpreted as logic state 0. After that, you have that signal conditioning, all that. Then you have this optical isolator. And then this particular state, that is 24 volt or 220 volt, is scaled down and conveyed to the processor as either a logic state 1 or logic state 0 signal. So the purpose of the input interface, one is to convert the high-level voltages that represent logic state 1 into a low-level voltage that is compatible with your processor. Two, very important, perform galvanic isolation between the field side devices and the processor. Three, provide a status display of the input. If the input is 1, some LED lights up. If the input is 0, no LED lights up. So these are the basic functions of an input interface. The output interface is just the opposite. So what does an output interface do? See, I've got a PLC. Again, you have multiple output interface lines. I'm talking about discrete, that is two state outputs. For example, you want to turn on a lamp, you want to turn on a solenoid valve, you want to turn on or off a particular motor. So again, this is a PLC, this is the output interface. You have multiple lines depending upon the number of devices that you want to operate. Again, if you want to say turn on a lamp, your lamp could be rated to 24 volt DC. You want to operate a motor that is rated at 220 volt AC. So none of your loads, whether it's a lamp or whether it's a motor or whether it's a pump, nothing operates at 3.3 volt AC. Nothing operates at 1.8 volt DC. But your processor generates a signal that is 1.8 volts to a maximum of 3.3 volts. So again, you need a hardware interface which does just the opposite. What does it do? It converts the logic states generated by the processor into a high-level signal. Again, typically 24 volts or 220 volts, or a third option is possible in case of an output interface. The output could be in the form of a contact. That is, if the processor generates a state of 1, then the contact is closed. And if the processor generates a state of 0, the contact is open. So the output state could be in the form of a contact. What is the advantage of having an output in the form of a contact? The advantage is, say if the PLC generates an output that is 24 volt DC, that is if the logic level is 0, the output is 0 volts. If the logic level is 1, then the output says 24 volt DC. That means in this case, the device which is connected to the PLC output should be rated for 24 volt DC. If you connect a 220 volt lamp to a 24 volt DC line, the lamp would not light up. And if you connect a 5 volt lamp to a 24 volt DC line, it will immediately burn out. So you need a load whose voltage rating matches the voltage rating of the PLC output interface. That means if the PLC output interface is rated for 24 volts, then you need a load which is rated for 24 volts. And if the PLC output voltage is rated for 220 volts AC, then you need a load which is rated for 220 volts AC. So that places a limitation on the load that you can connect to the PLC output. It should match the voltage rating of the PLC output interface. But the advantage of having a relay contact as the output is, again, the contact does not generate any voltage. It simply is a contact. It's either open or closed. It acts as a switch which is operated by the processor. So with the help of a contact, you can operate a load 5 volts. You can operate a load which is rated at 100 volts. You can operate a load that is rated at any voltage, because all you do is you take an appropriate supply voltage, connect your load in series, and connect the relay contact so that when the contact closes, your load is energized. When the contact opens, your load is not, it's de-energized. So having an output in the form of a relay contact is advantageous in the sense that it is flexible in terms of the voltage rating of the load that you can connect. You can connect a load that's rated for 24 volts. You can connect a load that is rated for 220 volts. All you need to do is connect a suitable supply in series. But if your output interface is connected as rated for 24 volts DC or 220 volts AC, then restricts the load that you can connect. If the PLC output is 24 volt DC, you have to connect a 24 volt DC load. If it's 220 volt AC, then you have to connect a load that is 220 volt AC. Then what's the disadvantage of a relay output? The disadvantage is a relay is a mechanical device, rather electromechanical device. So the maximum frequency at which the output can switch becomes severely restricted. If you have an electronic output, it could switch much faster. But when you have an electromechanical device, the maximum frequency at which the output could change state becomes limited. So this is a typical block diagram of an AC output interface. Again, you have the signal coming from the processor, which is at a very low voltage level. Again, standard, you have an this one LED. See here, you have got 8 LEDs. Here, the LED is representing the output status, the output that is being generated by the PLC. So if you find that here the status is 1, the LED is lit up, but finally the load is not operational, then you know there's something wrong with the load or something wrong with the wiring between the load and the PLC. So you can immediately diagnose that there's something wrong either with the load or with the interconnecting wiring. So here you have this logic. It's driven from the processor. You have an LED, again an isolator. Important to separate your low-level processor from the high-level field signals. Then you have a switching device. A switching device is a device which ultimately drives your load. It could be a relay. If the output is DC output, is a transistor driven into saturation or cutoff, and if the output is 220 volts AC, then the switch is a triac. Here, what is shown is an AC output module. So again, the optical isolator either drives this triac on or off. If the triac conducts, then your load is energized. If the triac does not conduct, your load is de-energized. So if the output is 24 volt DC, then instead of a triac, you'll have a transistor. If the transistor is saturated, then your load conducts. If the transistor is cut off, your load does not conduct. So basically what you have is a signal coming from the processor, goes through a stage of galvanic isolation, followed by an electronic switch, which could be a triac, which could be a transistor, or which could even be a relay. And then the final output from the device, you also have an LED representing the status of this particular device. Plus, additionally, in case of output modules, you require short circuit protection. Because what happens if your output load is short circuited? You need to protect your switching device. So in the simplest of cases, you either have a fuse. In case of AC modules, you have a fuse, which protects this particular triac in case your load is short circuited. And in case of DC outputs, that is 24 volt DC outputs, you have electronic protection. Probably you have seen electronic protection in the lab in your power supplies. If you short circuit a lab power supply, what happens is immediately there's an LED which turns red from green. Immediately the current output from the device is limited or restricted electronically. That is what is electronic short circuit protection. Because ideally, if you short circuit a voltage source, the current drawn is infinite. Because ideally a voltage source has zero source resistance. But if you draw a very large current from any electronic device, it will simply burn out. So if the output module is short circuited, you need to limit the current so that your output module or the output interface is not destroyed. So you need some kind of a short circuit protection, which in the simplest of cases is a fuse, or which could be some kind of an electronic short circuit protection, which is built into this particular output interface. So that is what is an output interface. This is the concepts of current source and sink. I'm not going into. Okay, let me make a very short. Look at this device. Here you have a lamp. PL1 is a lamp. This is a symbol of a lamp which is connected to an output module. This lamp is a DC lamp, and the switching device here is a transistor. Now see the connection? Some supply voltage which energizes the lamp connects to the output module. Inside the output module, the transistor is a switching device, and which ultimately connects to ground. So the transistor is cut off, no current is flowing through the lamp is not energized, or the output is not energized. And if this transistor is driven into saturation, then this behaves as a closed switch. So what happens is the current flows from the supply to the lamp, and this lamp is energized. But what is the direction of the current? See, the current is flowing into the output module, or technically it is said that the current is sinking into the output module. Sink or source basically signifies the direction of the current. If the current is flowing into your interface, it's called a sinking current. Here the current is flowing from the DC supply into the load into the input module. So this interface is actually sinking current. The opposite is this one. Here again, you have a DC supply. The switching device in this particular case is this. Now this is a PNP transistor, again driven into cutoff or saturation. Your load is now connected between the output interface and ground. So if this transistor is saturated, what happens is current from the supply flows through the transistor through the load into ground. Here, see the direction of current is from the output interface, out of the output interface into the load into the ground. So this is current source. And the previous one was current was flowing into the output interface, that is current sink. So this concept is important, the concept of current source and current sink, which determines whether the current is flowing into the output interface or the current is flowing outside the output interface. Here, what you see in this figure is an output module or output interface that acts as a current source. And previously, what you saw was a current sink. Here, the current is flowing into the output interface. So the output interface in this particular case behaves as a current sink. So this actually determines whether this other side of the load is connected to supply, other side of the load is connected to ground. See here, the other side of the supply of the load is connected to supply. So current is flowing into the output interface. The current is sinking into it. Here, the other end of the load is connected to ground. The current is flowing outside the output interface. So this is sourcing current. So depending upon the module, whether it is sinking current or sourcing current, you have to connect the load appropriately. That means the other end of the load is either grounded if this is a current source, other end of the load is connected to the supply if this is a current sink. So that controls or that determines the way you wire your output device. Whether you are connecting the other end to ground or are you connecting the other end to supply, it depends on whether this output interface acts as a current source or acts as a current sink. So the rest of it is much simpler. We have just talked about or spoken about discrete inputs and outputs. So the other option is analog inputs and analog outputs. Now, what is the analog inputs and outputs that are commonly supported? One is, of course, 4 to 20 milliamperes because that is what all transmitters generate. Second is voltage input. This is a current input. Second is a voltage input, which is typically either 0 to 10 volts or minus 10 to plus 10 volts. These are again standardized ranges for representing analog signals in industrial applications. And third is devices like thermocouples, which generate a directly millivolt output, devices like load cells, which directly generate a millivolt output, devices like RTDs, which generate a resistance, but using a constant current source, you convert this resistance into a low level voltage. So you have input interfaces which are capable of accepting 4 to 20 milliampere or 0 to 20 milliampere currents. Voltage is typically in the range of 0 to 10 volts, or inputs from sensors like thermocouples, load cells, or RTD converted into a voltage using a constant current source. So that is typically the kind of analog modules that you find within a PLC. So what's a block diagram? As you can expect, is the input voltage. Again, you have low pass filters and all that for suppression of noise. Now this analog signal has got to be converted into it's a digital equivalent. So what you need, again, as you can guess, is an A to D converter, typically either a successive approximation type or a sigma delta type, where the frequency of conversion is lesser, followed by an opto-isolator. That means the output of the A to D converter, remember, is logic level signals. There you have an optical isolator, which isolates your processor side electronics from the field side. So opto-isolator followed by your processor and the rest of it. Similarly, analog output modules is just the opposite. You have your processor. From the processor, you have opto-isolator, followed by a D2A converter. A D2A converter could either be generating a voltage or a current, which then finally becomes the output of the output interface. So it's typically a voltage signal, either 0 to 10 volt, minus 10 to plus 10 volts, or a current 0 to 20 milliamperes or 4 to 20 milliamperes. So that is typically what an analog output interface generates. So these are the different kinds of devices that be connected. For example, discrete inputs could be push buttons, limit switches, proximity sensors, temperature transmitters, and analog input, load a level transmitter, analog, pressure transmitter, analogs, and then you could have relays as outputs, motor contactors that operate motors. VFD is a variable frequency drive that is used to control the speed of motors in a continuous way, solenoid valves, and so on. You could have indication lamps, you could have sirens, and so on. There are different types of I/O devices that normally interface to PLCs. So this is the simplest of PLCs. Now you can see this LEDs. These are basically the LEDs that I was talking of, which represent the status of the inputs and the status of the outputs. You have a whole array of this where you have one LED per input channel. So this is the simplest of PLCs. This is what we have in your lab. It supports around, I think, 14 inputs and 10 outputs. So you have 14 LEDs on the top, which represent the logic states of the 14 inputs. And you have 10 LEDs at the bottom, which represent the state of the 10 outputs. So these are the typical. Plus on the this side, you will have different LEDs which represent the state of your CPU. Something has gone wrong with the CPU, something has gone wrong with the hardware of the system. They're all indicated using status lights, so that as malfunction, you can immediately identify something is wrong with this and you can replace this so that your system is again functional. And if you just open this cover, lower cover, this part is, there's a lid sort of thing. You can open this. Here you see this communication interface. This is a standard Ethernet interface, RJ45 connector. This is the interface that is provided on the PLC, which by default connects to your programmer. Optionally, this could be used for networking of PLCs. Optionally, this could be used for connecting a HMI display to your PLC and so on. And these screws are basically the point where you connect the inputs and the outputs. This is the input and output terminals. That is signals from the field devices connect here, and wires from these particular terminals lead to output devices. So these are the basically inputs and outputs that connect from field devices to this particular PLC. So now এখন একটা break দিচ্ছি to get your feedback. এরপরে next part is compact PLC and modular PLC. Now, what is a compact PLC and what's a modular PLC? সেই part is part 2, that is construction of PLCs. এখন অবধি আমরা যেটা basically discuss করেছি is what are the basic components, and with a little more emphasis on the input and output interfaces that is found on a PLC. The second is the construction of the PLC. মানে প্রথম যে ছবিটা দেখিয়েছিলাম, mounting system. This is again an important consideration because this is what differentiates between what is a compact PLC and what's a modular PLC. But before I go into that, I think I'm already at saturation level. মানে তোমাদের point of view থেকে বলছি, তাহলে কি এখন একটা ব্রেক দিয়ে আগে ওই দেখে নেব ফিডব্যাকস গুলো নাকি, মানে প্রেজেন্টেশন গুলো না কি করব? হ্যাঁ, সেটাই করে নাও। হ্যাঁ, কেউ দেখাবে? হ্যাঁ,
sir, please stop the presentation.
sorry, yeah.
हाँ, चुपचाप रहो. So is it visible?
Yeah.
Okay. I have made tank filling version 2.
What's your roll number?
5. Sir, currently it is in manual mode. This is the tank. TL I have marked as 20 and TH I have marked as 80%. These are the two. I adjust the values of Q in and Q out through these two potentiometers. So at this instant of time, I have 17.82 liter per second as the input flow rate and 6.56 liter per second as the output flow rate. Now, if I start the motor, it is in manual mode. So now if I start the motor, it is going up. Here I am showing the level, and here I am showing the transmitter output. Yeah, it's manual mode is done. Now, if I go to auto mode, since it is between TH and TL, the pump is not started. as soon as it reaches TL, the pump has started. Uh, when it reaches TH, the pump has stopped. Now, for the next time, if we assume that there is some leakage in the pipe or and all, I mean, I'm decreasing this. Um, no, I've set the timer to be 20 seconds for it to wait uh, if the water is increasing or not.
What is the other knob?
Sir, Q out and this is Q in. It is written here. Input flow rate, output flow rate of the tank. Yeah, 20 seconds have elapsed. So we have got a safety interlock alarm and the pump has stopped. The water, uh, since Q out was there, the water drained out. Now, if I acknowledge it, yeah, it is again working. Oh, I have to increase. Sorry, I didn't increase it. It's working. If there is an overload, the pump will stop. Then, if I increase, then if I rectify the overload situation, the pump again starts when it reaches TL. So is it okay?
The overload option again?
Yeah.
Now, after that, what you will be doing?
Sir, if overload is there, then the pump won't start. And I just rectified the overload situation. So pump is starting.
No, but what about the acknowledge and reset button?
So acknowledge and reset button was for the safety interlock alarm. Now, as far as in the problem.
No. It was for all the three problems.
Oh, okay. So I have to change it now.
That can easily implement. No.
Okay. Okay, sir. It is over from my side.
Okay.
Anyone else?
Sir, can I present?
Yeah.
So this is tank filling version 2. So currently it is in manual mode. And
what's the roll number?
Start the so roll number 32. So okay, so if we start the motor, yeah, tank is filling. And we can hear, we can see the water in the tank in here. So timeout has occurred. So we acknowledge it and so we acknowledge it and we reset it. So the motor restarts and the motor goes above TH as it is not in auto mode. So let us suppose there is a leakage and we increase the leakage. So
but where is the tank?
turn off the motor. So here it is. The tank percentage is given in here. So currently it is in 80% full. So and TH integrator is in here and TL integrator indicator is in here. So there is a leakage and the water level is going down and motor is off. So let us suppose now it is in auto mode. So the motor will not start as the water is above TL. So once the water goes below TL, the motor starts. And timeout has occurred, so we acknowledge it and reset. Let us make the leakage 0. Again, timeout has occurred. Let us acknowledge it and reset it. Timeout was for 8 seconds. 8 seconds of timeout will occur. So as the water reaches TH, so motor turns off in auto mode. So let us now check for if the sump is empty or there is an overload occur. So let us make the leakage as 5.
Can the outflow be controlled in your system?
Nah, actually, I didn't made anything.
Okay.
So I can add that if you want.
But no, outflow is always maximum. What have you considered? Outflow is always maximum.
Oh, actually, no, I have not considered anything about outflow.
No, but then how's the work? Level coming down if you have not considered
So
anything.
using leakage, there's a leakage dialer in here. So leakage is controlled. So if you want, I can just make this leakage as outflow.
Actually, leakage means when you're filling the system.
Acha. Oh, leakage was in the pipe.
Yeah. Leakage means when you're filling the
Sorry.
system.
I thought the leakage was in tank, so the leakage speed can vary.
Okay, fine.
I can just make that if you want.
Okay, it's fine. It's
Assume
fine.
is that leakage is the output.
Okay, sir. You can consider leakage as outflow.
Mhm.
Okay, sir. Thank you.
Who is next?
স্যার দেখাবো?
হ্যাঁ দেখো।
স্যার দেখা যাচ্ছে কি?
যাচ্ছে।
স্যার প্রথমে স্যার লিফটে স্যার প্রথমে এটা স্যার গ্রাউন্ড ফ্লোরে আছে, তো এটা থার্ড ফ্লোরে স্যার স্যার প্রথমে স্যার এটা হচ্ছে হলো স্যার লিফটের স্যার যদি ওপেন থাকে তাহলে স্যার এটা রেড লাইট জ্বলবে, আর যদি ওপেন না যদি বন্ধ করে দেওয়া হয় তাহলে স্যার এটা উপরে যাওয়া শুরু, দ্যাট মিনস কোন ফ্লোরে যাবো সেটা যদি ক্লিক করি সেখানে যাওয়া শুরু করবে। অ্যান্ড সেকেন্ড ফ্লোরে যেতে চাই তাহলে সেকেন্ড ফ্লোরে চলে আসবে। যদি স্যার সেকেন্ড ফ্লোর থেকে কেউ উপরে যাওয়ার জন্য কল করে, অ্যান্ড থার্ড ফ্লোর দিয়ে যদি কেউ নিচে যাওয়ার জন্য কল করে, ফার্স্ট কল প্রেফারেন্স হবে, যে আগে মানে ক্লিক করবে সেখানে আগে যাবে। এবং স্যার সেকেন্ড ফ্লোর থেকে যদি ফার্স্ট ফ্লোরে যাওয়ার যেতে চায় তাহলে ফার্স্ট ফ্লোরে ক্লিক করলো, তো প্রথমে থার্ড ফ্লোরে যাবে, থার্ড ফ্লোর দিয়ে স্যার ফার্স্ট ফ্লোরে চলে আসবে। স্যার কিছু জিজ্ঞেস করুন স্যার।
ঠিক আছে।
তুমি নিজে বানিয়েছো?
হ্যাঁ স্যার।
কোথায় কপি করেছো?
কপি করিনি
কোন সাইট থেকে কপি করেছো?
স্যার, কপি করিনি স্যার এগুলো। স্যার এটা স্যার এইগুলো স্যার ইন্টারনেট দিয়ে নিয়েছি, ভিজুয়ালাইজেশন তো ইন্টারনেট দিয়ে স্যার করেছি, ইমেজ পুল দিয়ে স্যার নিয়েছি। স্যার 28 রোল নাম্বার।
ঠিক আছে।
স্যার দেখাবো?
দেখাও।
ঠিক আছে, ও দেখিনি, তারপর দেখাচ্ছি।
রোল নাম্বার সিরাজ, রোল নাম্বার।
Hello, sir. Sir, am I audible?
What's the roll number?
Sir, 36. So these are the button inside the lift, and And so these are the button on the floor. So suppose if someone wants to go on the top floor, that is the third floor. So if someone is calling the lift on the third floor, so the lift reached there and the gate gets automatically open. Now he wants to go down the floor. Suppose he wants to go on the ground floor. So these are the button inside the lift. Oh, okay. Wait. The gate is not closed yet. Sir, is it okay? So suppose someone on the second floor called the lift. Gate closes. And then he wants to go on the first floor. Oh, sorry. Sir, anything else?
The gate has to be manually closed.
Yes, sir. Sir, but it gets open automatically.
Okay. Take to the ground floor.
Ground floor.
Ground floor is one or two, one or zero.
Sir, zero. Ground floor is 0. First floor is 1. Second floor is 2, and third floor is 3.
So 2 wants to go up and 1 wants to go down.
Okay. 2 wants to go up. Wait. I have to close the door. Shit. Wait, sir. Two wants to go up and 1 wants to go down. Sir, it will stop on the first floor first.
This is not the best of logic, right?
Yes, sir. But I tried.
Okay.
So should I stop sharing?
Yeah.
And what is this? How many pixels does your lift move? When you
Sir,
move to
100, sir.
100, actually.
So should I stop sharing? Thank you, sir.
হ্যালো, দেখা যাচ্ছে? হ্যালো, আরে ধীরাজ মাইক অফ করনা थोड़ा। হ্যালো, হ্যাঁ স্যার, দেখা যাচ্ছে? ঠিক আছে, দেখা যাচ্ছে। মানে এটা হচ্ছে গ্রাউন্ড ফ্লোর, মানে এই পাশটা আমি সুইচ দিয়েছি, দিইনি, ওই বাটনস দিইনি। ঠিক আছে, মানে বাটন দিয়েছি, সুইচ দিয়েছি, মানে লাইট দিই, ঠিক আছে, এগুলো দেখ গ্রাউন্ড ফ্লোর ফার্স্ট ফ্লোর এগুলো দেখানোর জন্য। তো ধরুন আমরা এখন গ্রাউন্ড ফ্লোরে আছে, ফার্স্ট ফ্লোরে যে আছে সে নিচের দিকের জন্য টিপেছে, সেকেন্ড ফ্লোরে যে আছে সেও নিচের জন্য টিপেছে, থার্ড ফ্লোরটা এরকম টিপেছে, তাহলে ও ফার্স্ট ফ্লোরে দাঁড়াবে না, সেকেন্ড ফ্লোরেও দাঁড়াবে না, একবারে গিয়ে থার্ড ফ্লোরে দাঁড়াবে। ঠিক আছে, এবার সাপোজ ও যখন থার্ড ফ্লোরে পৌঁছাচ্ছে তখন সেকেন্ড ফ্লোর কি উপরে যাওয়ার জন্য টিপেছে, তাহলে ও নামার সময় এখানে দাঁড়াবে না, ও ফার্স্ট ফ্লোরে নাম, ও সরি সেকেন্ড ফ্লোরে দেবা আছে, তো এমনি দাঁড়াবে, নাম দাঁড়াবে, ঠিক আছে দাঁড়াবেই। সাপোজ এখান থেকে যারা চেপেছে তাদের মধ্যে কেউ গ্রাউন্ড ফ্লোরে যেতে চায়, তাহলে গ্রাউন্ড ফ্লোরের জন্য এটা হচ্ছে লিফটের ভেতরের বাটন গুলো, আর এটা হচ্ছে বাইরের গুলো, ঠিক আছে। ফার্স্ট ফ্লোরে যে টিপেছে
বাঁ দিকে চারটে সুইচ,
ওটা হচ্ছে লিফটের ভেতরেরটা,
ডান দিকে চারটে সুইচ কি?
ডান দিকে চারটে সুইচটা জাস্ট কোন লেভেলে লিফটটা আছে ওটা ইন্ডিকেট করার জন্য, মানে এটা লাইট দিলে ভালো হতো অ্যাকচুয়ালি, আমি সুইচ দিয়েছিলাম তখন ভুল করে। মানে এটা ধরুন গ্রাউন্ড ফ্লোর, মানে এটা উপরের দিকে অন দেখাবে, ঠিক আছে। হ্যাঁ ঠিক আছে, এবার মানে ধরুন এইরকম কন্ডিশনও আসতে পারে যে ধরুন একজন মানে ফার্স্ট ফ্লোরে দুজন মানে দুটোই টিপে দিল কেউ, ঠিক আছে, এবং ও তখন ফার্স্ট ফ্লোরে গেল, হ্যাঁ মানে সাপোজ দুটোই টিপেছে, কেউ 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 উপরে যেতে চায়, কেউ কেউ নিচে যেতে চায়, তখন ইন দ্যাট কেস আমি ওই প্রায়োরিটিটা নিজে সেট করেছি, লাইক গ্রাউন্ড ফ্লোরকে সবসময় প্রেফারেন্স দিয়েছি, কারণ একসাথে চেপেছে, অন্য কোনো দিকে প্রায়োরিটি দেওয়া নেই, জাস্ট কিছু লোকে উপরে যেতে চায়, কিছু লোকে নিচে যেতে যায়, এরকম কন্ডিশনে ও আগে নিচটাকে প্রেফারেন্স দেয়, বিকজ আমি টাইম ডিলেটা এটার জন্য কম দিয়েছিলাম, ঠিক আছে। এবার এরকম কন্ডিশনেও যদি কেউ সাপোজ আপের জন্য যেতে চায় তাহলে ও এখানে এসে থেমে যাবে, কারণ সেকেন্ড ফ্লোরে যখন পৌঁছেছে তখন ওটা আপ ছিল, কিন্তু আপ দিয়ে যদি সে এবার নিচে যেতে চায় বাই এনি চান্স, তাহলে সেটাও মানে কনসিডার করবে, লাইক মানে কেউ আপ বাটন দিয়েছে কিন্তু তারপরে নিচেও যেতে চাইছে, লাইক সেটাও কনসিডার করবে, ও গ্রাউন্ড ফ্লোর পর্যন্ত। তো এতটাই, আর কিছু আছে?
থার্ড, আচ্ছা এবার থার্ড ফ্লোর উপরে যাবে আর সেকেন্ড ফ্লোর নিচে যাবে একসঙ্গে?
থার্ড থার্ড ফ্লোর থেকে তো কেউ উপরে যেতে পারবে না।
ও থার্ড না, আচ্ছা ওটা তোমার কি, ওটা গ্রাউন্ডে আছে, সেকেন্ড ফ্লোর উপরে যাবে আর ফার্স্ট নিচে যাবে।
ঠিক আছে, ও ফার্স্ট ফ্লোরে দাঁড়াবে না, কারণ ও সেকেন্ড ফ্লোরে যাবে, কারণ এটা নিচে উপরের মোশনে আছে, এটার পরে ও নিচে নামবে first floor এর জন্য।
ঠিক আছে, কিন্তু যাই হোক তোমার লিফট পজিশন ডিসপ্লেটা একটু অড হয়েছে।
মানে এই লিফটের এই বাটনটা,
না না, পজিশন ডিসপ্লে, হ্যাঁ।
আচ্ছা মানে এইগুলোকে লাইট দিলে ভালো হতো না?
লাইট না, তোমার যেটা দেওয়ার কথা ছিল হলো ওইটা রিড আউট, আর
Read
তোমার
out?
এইটা জাস্ট যখন এক্স্যাক্টলি গ্রাউন্ডে তখন ওইটা অ্যাক্টিভেটেড হচ্ছে।
কোনটা?
এবার ধরো গ্রাউন্ডটা ফার্স্টে মাঝখানে থাকলে কি হবে, কি দেখাবে?
তাহলে কোনোটাই অ্যাক্টিভেটেড থাকবে না, কারণ
না, তাহলে এবার তাহলে আমি অন্য ফ্লোর থেকে কি বুঝবো লিফট কোথায় আছে?
গ্রাউন্ড আর ফার্স্ট ফ্লোরের মাঝে থাকলে কোনোটাই অ্যাক্টিভেটেড দেখাবে না, মানে
হ্যাঁ,
ধরুন
কিন্তু
এটা তাহলে সবগুলোই বন্ধ থাকবে, লাইক
হ্যাঁ,
লিফট
কিন্তু
মাঝে
নর্মাল
কোথায়।
লিফটে তোমার সবসময় পজিশনটা দেখায়।
ও হ্যাঁ হ্যাঁ,
গ্রাউন্ড থেকে ফার্স্ট হলো গ্রাউন্ড যখন উঠছে, আর যখন নামছে তখন ফার্স্ট থেকে গ্রাউন্ডটা ফার্স্টই দেখায়। যাই হোক, ঠিক আছে। তোমার রোল নাম্বার কত ছিল?
ঠিক আছে, আমার রোল নাম্বার 73। স্যার ঠিক আছে এমনিতে মানে,
ঠিক আছে,
হ্যাঁ ঠিক আছে।
এগুলো সব কিন্তু পাঠাতে হবে, হ্যাঁ।
হ্যাঁ পাঠিয়ে দেবো, হ্যাঁ ঠিক আছে।
স্যার দেখাবো স্যার।
হুম।
এখন স্ক্যানিংটা বন্ধ করো। প্রতীক ও নিজের মনে কাজ শুরু করে দিয়েছে। প্রতীক তোমার শেয়ারিংটা বন্ধ করো। কে একজন প্রতীককে ফোন করে বলো, শুনতে পাচ্ছি না। বললাম তুমি বন্ধ করে দিতে পারো না, বের করে দিতে।
আরেকজন শেয়ার করলে চলে যায় না? আরেকজন শেয়ার করলে কি হয়?
ও আচ্ছা, হ্যাঁ।
প্রিয়াঙ্ক, তুমি শেয়ার করার চেষ্টা করো তো, দেখা যাক কি হয়।
ওকে স্যার।
না, আমি শেয়ার বন্ধ করতে পারি না, তাহলে একদম ওকে বের করে দিতে হয় ক্লাস থেকে আর কি, সেটা পারি।
দেখা যাচ্ছে স্যার।
হ্যাঁ, আসছে।
স্যার ট্রাফিক সিগন্যাল ভার্সন 1 and 2 স্যার।
রোল নাম্বার
স্যার 2001। ডেফিনেটলি 2001। স্যার ফুল রোল নাম্বার বলতে হবে?
না না, ঠিক আছে।
স্টার্ট করুন। এটা স্যার হচ্ছে ডে মোডে হচ্ছে, আর হচ্ছে এবার হচ্ছে মোড চেঞ্জ করতে নাই, হচ্ছে ব্লিঙ্ক মোড। ঠিক আছে। এটা হচ্ছে 3 আর 4। ঠিক আছে স্যার। স্যার মিল্ক ব্লেন্ডিং মেশিনটা এটা। ইনক্রিজ করছি 3 লিটার অব্দি ইনক্রিজ করতে পারবে। স্যার ডিক্রিজ বাটন ডিসকানেক্ট করছি। হোল্ড বাটন প্রেস আছে, ডিসকানেক্ট হবে না। হোল্ড বাটন ক্লিক করলে ডিসকানেক্ট 0 অব্দি হবে। হোল্ড ঠিক আছে স্যার। একটা হচ্ছে মোটর অপারেশন একদম মানে বেসিকটা করেছিলাম স্যার, দেখাবো? দেখিয়ে দাও, আগে যদি না দেখিয়ে দাও দেখিয়ে দাও। স্যার একটু ল্যাগ হচ্ছে। যতক্ষণ ওয়েদার আছে
তুমি কি 3 সেকেন্ডের ব্যাপারটা ইমপ্লিমেন্ট করেছো?
না স্যার, এটা তো স্যার বেসিকটা।
আচ্ছা ঠিক আছে, ঠিক আছে, ঠিক আছে।
নেক্সট কে দেখাবে?
শেয়ারিং, স্যার শেয়ারিংটা কি বন্ধ হয়েছে?
হ্যাঁ তোমারটা বন্ধ হয়েছে।
কারণ স্যার আমার তো এখান দিয়ে দেখাচ্ছে না।
হ্যাঁ, নেক্সট যে করবে চলে এসো, শেয়ার করো, তাহলেই হয়ে যাবে।
স্যার আমি কি বেরিয়ে যাবো?
হ্যাঁ, চলে যাও।
স্যার আমি হ্যালো
হ্যাঁ, যে কেউ শেয়ার করো।
হ্যালো হ্যাঁ স্যার। স্যার ট্যাঙ্ক ভার্সন 2টা। স্যার ইনিশিয়াল কন্ডিশনে সাম খালি আছে, যার জন্য সামের লাইটটা অন আছে অ্যান্ড বাজারটা বাজছে বিকজ অফ সাম খালি বলে, আর অ্যালার্মটা ইন্ডিকেট করছে। তো আমি যদি অ্যাকনলেজ অ্যান্ড রিসেট করি তাও ওটা কন্টিনিউ হতে থাকবে, কারণ সামটা এখনো ভর্তি হয়নি। তো সামটাকে ভর্তি করছি, সামটা ভর্তি হলো, সামের এগেনস্টে একটা ইন্ডিকেটর দেওয়া আছে, সামটা ফিল আপ হয়েছে সেটা দেখাচ্ছে। তো ম্যানুয়ালি ম্যানুয়াল মোডে দেওয়া আছে, দেওয়ার পরে ম্যানুয়ালি স্টার্টটা করছি আমি। তার আগে অ্যাকনলেজ রিসেট করে নিলাম, ম্যানুয়ালি মোডে দেওয়া ছিল যার জন্য এটা স্টার্ট হয়ে গেল। দেন স্যার ট্যাবটাকে আমি ওপেন করে দিচ্ছি।
রোল নাম্বার কত?
স্যার 2004। অ্যাকনলেজ রিসেট, আমি স্টার্ট নিয়ে নিলাম। দেন স্যার সামটাকে আবার ফিল আপ করে নিলাম, ট্যাবটাকে অফ করলাম, অ্যাকনলেজ রিসেট, ম্যানুয়ালি স্টপটা করে নিলাম। দেন স্যার ফ্লোরেটটা 5 দিয়ে দিলাম, জলটা কমছে।
ঠিক আছে, মানে এটা কোথাও রিকোয়ারমেন্ট ছিলই না আর কি, এটা করতে গেছে বোঝা যাচ্ছে।
হ্যাঁ
ছেড়ে
স্যার,
দাও, বন্ধ করো। এই সাম ফর্মে গল্প করতে পেলে ছিলই না কোথাও গল্পগুলো,
আমি
যেহেতু আগে একজন করেছে ওসব কারোর মাথা থেকে বেরিয়েছে, তারপর গোটা 10 ওই এক জিনিস হয়েছে। আচ্ছা ঠিক আছে।
স্যার অটোমোটিভ হচ্ছে আমার 20 ইয়ার্স আর 9।
না অটো দেখাতে হবে, বোঝা গেছে, ওটা বোঝা গেছে একই। হ্যাঁ একই জিনিস আমরা 10 বার দেখে নিয়েছি, আর নতুন করে অটো দেখাতে হবে না, ছাড়ো। আর কিছু থাকলে দেখাও, নাহলে ছেড়ে দাও।
না স্যার আমার লিফটিং বাকি এখনো হয়নি।
ঠিক আছে।
Hello, sir.
হ্যাঁ
Sir, it's me, Musibul. Actually, I made the changes about that output and leakage. Can I present again?
ঠিক আছে, it's understood, fine, not necessary
Okay.
really.
Okay, sir. Thank you, sir.
কে প্রেজেন্ট করবে?
স্যার আমি প্রেজেন্ট করব?
হ্যাঁ করো না।
স্যার এটা কুইজ মাস্টার ভার্সন 1টা।
রোল নাম্বার?
রোল নাম্বার 67।